Hi, I'm Peter Haddock, and I'm here at Perkins Engines for another episode of Discovering the Power of Perkins, my series, which is really looking deep down into what they're doing here and around the world with customers. And I'm joined by Tim Ward, computational fluid dynamics expert. Tim, what on earth does that mean, and what do you do?
Yeah, so I'm the thermofluids simulation team manager here at Perkins, and yeah, we work in the field of computational fluid dynamics. And that's essentially using computers to help us understand and model fluid flows.
So really what we're talking about here, folks, is we're talking about all the different aspects that I want to cover, which are things like, you know, how do we get the fluid into the engine and get it combusting, oils, coolants. We've also got things like after treatment and things like that that all come into these flows and cycles that you see on the screen next to us. So, Tim, tell us first of all, you know, the most important thing with all of this is how fluids move around the engine when we've got it physically in a machine. And of course, it's very difficult to understand how that works unless you have clever simulation, folks. So tell us about that and how it works.
Yeah, so essentially, I guess one of the values of being able to do simulation is we can see inside an engine. So in my example, we can see the fluid flows inside the engine, so we can optimize them to get them right first time. Certainly at the very early stages of the design process, and we can be there working with the designers, simulating things, making the fluid flows what we want them to be, giving us the right performance, and essentially making it so that when we cut the hardware and we test them on the engine test beds, that they should work right first time. That's the intention.
Yeah, the first thing with this, Tim, we've got stage 5 engines here. They've been made smaller yet more powerful. All these different things depend on how we get the fuel first into that engine. So we've also got tiny weeny injectors now that you've just told me earlier need to be pointed in the right direction or oil goes a bit sooty. So how is that all put together and why is that important? What happens?
So we have the ability to simulate the combustion process, and that is kind of the heart of the engine. You know, that's where the power is generated. So we can simulate various different scenarios, different configurations, different concepts to tune the shape of the piston. We've got one here, for example, and we've got an injector here.
Right.
But we can tune those and look at lots of different scenarios very easily, very quickly, and understand what effect that has on the engine from a performance point of view, from an emissions point of view, and also from an oil sitting point of view, if you're combusting gases close to where the oil is.
So I never knew about oil sooting, and oil sooting means that you're damaging the oil that you need, you know, in the engine to lubricate it.
Yep.
So when you inject in the wrong place and near to where that oil flow happens, what causes that oil sooting? Is it heat or what happens?
Well, so during the combustion process, soot is generated.
Yeah.
And if any of that soot gets onto the oil, which is on the cylinder walls, it can then be pulled back down by the piston and then taken into the oil in the sump. And that would age the oil prematurely, meaning that you'd have to change your oil sooner.
And part and parcel of where we've got to with all the stage 5 engines now from Perkins is actually we've extended the life cycle of maintenance. So this part is absolutely critical that you get that right and you get that injector over here, folks, doing their job. So that enables us to go through the first most important thing. How do we inject the fuel? How do we protect the oil? How do we make the power? But then there's other things you were telling me about, Tim, that actually talk about other fluid movements around the machine. So let's go and talk on about that. The next one I'm quite interested in is coolant.
Okay.
Because you get coolant literally filling up within an engine. And you said there's a little bit of a problem if you get it wrong because air gets in the way. Tell me a little bit about that.
That's right, yeah. So in the engine, we've got lots of coolant passages to keep it cool, to control the temperature. Yep. And as you can imagine, as you fill it, you could get air trapped. Yep. So because you can't see this happening in the engine, you just assume it would fill. Yep. But obviously it doesn't, or sometimes it doesn't. So we can simulate the coolant rising, the coolant filling, and we can identify where these risk areas are, where the air might get trapped, and then we can work with our designers to improve the design of that so that the air can evacuate as it's filling. And if we don't get that right at the very start and we find out too late on, there's a lot of rework, a lot of redesign, which then has a massive impact on the time and cost of our engine programs. And also our customers wouldn't want to receive their engine in a machine and they fill it up, and then they move about and they find out their coolant level's dropped and they have to go and top it up. So we try and do all this simulation to try and mitigate and remove those risks.
And who'd have thought that through simulation you could push air out in the right way? You know, that little turn that might be that little area where the pockets form,
exactly,
or they don't want to be pushed through. All fascinating elements, because your design and the simulation you go through at the start all goes through to the next phases of all the testing, all the engines and everything that go through. Of course, we said coolant there, right? So sometimes we're working in very, very hot, and sometimes we're working in very, very cold conditions. So the actual coolants that you need to use in those areas are different. I've been into the cold chamber, folks, where we actually had some fluids that literally looked like ice cream sorbets when they're in the wrong temperature. Because again, you're simulating the stuff in here, but you're also simulating how those oils and coolants flow when we're at these different temperatures, aren't you?
That's right. Yeah. So for the oil system, we have models, the system models, which bring all the components together. So if you can imagine, for the oil system, you've got a pump, you've got a turbocharger that all need oil, and they all move all around the system. And in isolation, you can understand how they work, but pulling them together as a system and understanding how one component affects another is a big deal. So in the cold chamber, for example, we can simulate the oil flowing through all of these components, seeing what the pressures are around the system, how long it takes the oil to get from the sump all the way through to these components, and we can do that at lots of different temperatures with different viscosities of oils, as you saw in the cold chamber. And again, we can do this very quickly in simulation and get the design aiming for right first time before we go and do those tests, so that we can minimise the amount of testing we do there, and that reduces the cost.
Yeah, and overall what we're then seeing is giving people that guideline as well, to say, you know, they've got a fluid guideline at Perkins here, folks, but to say when we do get down to those temperatures, if we have extreme conditions, extreme heat in the UK or extreme cold in other areas of the world, you've got that ability to say these are then the types of coolants and the types of fluids we need to use at those points, which is critical to those people keeping their engine moving, isn't it?
Exactly, that's right. Yeah, it's exactly that we define everything right, and through simulation we can help understand these bounds and set these guidelines.
But an engine, it might be the heart of the machine, folks, but an engine has got loads of other tasks to do. So there's loads of other things that your customers like to sort of bolt on to the engine. So, you know, one of those cool things that we all need right now is actually air conditioning, cab cooling technologies that help us to keep cool and warm in the different temperatures. That's an add-on, though, isn't it, to the engine? Again, another simulation moment, isn't it?
That's right. Yes, this is on the cooling system. So we have our models of the engine, and if a customer comes along and says they would like to attach their cab heater or air conditioning system, like you say, we've got the ability to connect those up in our simulation models, understand what effect that will have on the core engine cooling, and see if we can provide the right amount of flows into that component, to then understand, can that meet the customer's needs, or can we make some changes to help support the customer? Because if we don't get that right, then, you know, we could impact the engine's performance. And also, if we were to do that on a machine, on an engine, that costs a lot more money, a lot more time, because you've got to make components to try it. But the value of simulation is we can look at it virtually and provide that guidance.
And so the next element for me, though, is all about emissions, and it's all about exhausts emissions, and it's all about the after treatment. So the first thing, you know, we talked about earlier was about how we look at the engine and the performance and make sure that, and when we're taking emissions out of the engine, then into the after treatment, we get that bit right. So the exhaust recirculation is an important other movement, isn't it?
It is, that's right. There's an image here on the screen actually of that. So
right there,
for part of emissions control, there's an amount of exhaust gas that we recirculate back into the intake.
Yep.
But it's important that when that gas comes in, it mixes well. And again, on an engine, you can't see this, and it happens so quickly, you can't understand, is it actually mixing properly, or does a lot go down one cylinder and not down others? So again, we can simulate this, understand have we got an equal amount of exhaust gas coming into our cylinders along with the fresh air, so that we've got an equal balance. Because if there's an imbalance, then you could get an imbalance in the emissions that are created that then ultimately come out of the engine.
And it's those emissions that with stage 5 are so critical, because obviously the one thing you do here as well, and I've seen it, is actually you retest the engines that you've created with the previous emission standards, now with the new emission standards, to see that they're still performing 2 to 3 years down the line. And that's really important from that perspective, because when we see how you can model this, we can see that you can build in that robustness to that element. The other thing for me then, folks, is we all talk about after treatment now, and you know, the after treatment systems that you can develop now here with the smaller engines mean that you can actually put those engines and smaller engines into equipment that can be a compact radius and a smaller piece of equipment, but still needs the hydraulic power, for example. And so the after treatment is not necessarily something people think about when they look at the flows, but it's critical now, isn't it?
It is, yeah, that's right. So again, we can do a lot of work on after treatment, understanding what the pressure drop is through the system, and what restriction that has, and what impact that will have on our engine, because we design and develop our engines to a certain requirement, and if the after treatment system doesn't meet that, then the whole system won't work together. But then we can help support our customers in modelling and understanding the flow through their systems, and to see what impact that does have on the engine, and can they work together, and if not, we can then support them to help redesign and come up with a solution.
And this is what it's all about, folks. We're working in a global industry here. We're working in the heat, in the cold. We're also working with big engines, small engines, different types of applications that require different power ratings. And all of this can be simulated effectively so that we can have those extended life intervals for maintenance, so we reduce the cost, we're reducing the environmental impact if we keep the oil in good nick because we're spraying the fuel in the right direction. When we get everything cool for the operator of the machine, they're really happy. So all of this stuff adds in, and the whole element of this whole fluid analysis process means that we can get things right first time, and then everybody benefits. And fundamentally, it's a perfect example of why we need to concentrate on these types of things, get the right fluids in the first place, put them into the engine, make sure it's all managed, and let that computer, that engine computer, actually change and optimize the different processes. And this is the final bit of it, isn't it? Because if a customer wants to use your engine in a specific application with other bolt-ons, you can actually help them design and optimize that engine for that particular machine, can't you, with all the fluid elements here as well?
Exactly, yeah. We work very closely with our customers, so when these new options come in, and we can use all of our suite of simulation tools, all our existing models that we've got to help meet the needs for their machine.
So folks, we need to push the air out, tick that box. We need to keep cool with the coolant doing it properly, tick that box. We need the fuel to be in the right way, tick that box. We need the oil to be looked after so it has its longer life. And we all, therefore, need to look after our fluids and be a bit more dynamic as we look at that approach. So great to see you today. Thanks for telling me all about this clever simulation. Cheers.
Thank you.